So first of all, in the last week, we have learned about the magnetic materials. So let me write down some things here for easier revisions. Okay, so we know that different materials has different performance when it is applied with the magnetic field. So we call the materials magnetic materials. Each magnetic materials. So concerning each magnetic materials, there are several concepts that need to be remembered. One is the magnetizing force, which usually using the H represented. The other one is the magnetic field produced by the magnetizing force through the magnetic materials. That is the magnetic field density. That is the B. Okay, as I just said that B is produced by the H on the materials. So the relationship you should know that the B, so magnetic permeabilities sorry. Permeabilities, okay. That's mu, okay. Permeabilities, mu. So the relationship is the flux density over the magnetizing force. Okay, so once again, so any magnetic materials has its unique, permeability, mu. If you apply a magnetizing force, H, on the materials, then there is a magnetic flux density, B, produced in the materials. So the magnetic materials permeability mu is the ratio of B over H. That's the nature of the magnetic materials. Remember, this is the key words of the magnetic circuit. Okay. Okay, this is the key. Okay, so we have magnetic field in the world because this one, because mu, right? Because mu. So when there is current, there is a magnetic field. The mu, right? So in the free space is a constant, that is the mu zero. In any materials, it is equal or larger than mu zeros. Okay, so that's why we have so-called the mu equal to mu relative and mu zero. Okay, so mu zero is the universal constant, at least in the world we are living now. Okay, so probably there are multiple universe we don't know. Okay, but mu zero is the universe constant in this universe. Okay, and therefore we have the magnetic field everywhere. Okay, everywhere in the universe. Okay, where there is current, there's this one. This is the key. As a matter of fact, right, in the magnetic circuit, the key issues is that to find out the permeabilities for each parts of the circuit. Then you can determine whatever you want. Okay. So that's the key. In practice, the mu has been obtained by doing experiments. In the experiments, we can apply the current that is the proportional to the H. Then we can measure the induced voltage across the materials that is proportional to the flux density B. So H more or less related to the current. So B more or less related to the voltage. Look at here. So therefore, we have so-called BH curves. BH curves. So H, magnetizing force, magneto-motive force, the currents, they are proportional to each other. And the flux density, flux, and the induced voltage, they are proportional to each other. So that's the BH curves. Based on the BH curves, one can determine that's the permeabilities. Now, so as shown by these figures, if you at the beginning increase the currents, generally that means increase the H, then you will find that B increase. So they increase along a certain path. For example, the path shown here. However, when the current decrease, when the current decreases, then you found that the magnetic flux density B does not decreases along the same path as it increases. So and so on. Finally, when the current change in a cycle like AC currents, then they form a so-called BH loop. BH loop. This BH loop, because the periodical change of the current, therefore periodical change of the H and periodical change of the B. So the BH periodically changing, but not follow the same path as the beginning. So therefore there is a loop. This loop we call it hysteresis loop. So this is also showing you that the mu, which is the ratio of the B over H, actually is changing with the values of the H, which is not a constant. So that's the limitations of the definition of the mu, because the human beings have no means to identify the mu's analytically. We have to get the mu by doing experiments. That's the scientific research. What's it? It's not a theory. It is just based on observations, based on experiments. So do not thinking that any formulas is a mystery. It is just based on experiments. Do not trust the so-called theory, trust experiments. So this formula itself is just descriptions of the experiments, and which is not a constant. So it is the mu that changing with the current, making that the analytic analysis of the magnetic circuit impossible. So at each step we have to confirm the mu. Later on, in the tutorial examples, we will show you how to determine the mu, So anyway, by this chance, we have a thorough revision on the magnetic materials. Particularly, we have emphasized the concepts of permeabilities, which is changing with current. And also, in practice, when you're doing the experiments for getting the BH curves, you'll find several phenomena. Here, introduce you two. One is the hysteresis loops. The other one is the eddy current losses. So hysteresis loops, eddy current losses. Eddy current losses are explained in the last week, and by drawing some things there. So you're understanding that because that each of the so-called magnetic pole that is corresponding to a small ring currents in the materials. So each of the ring currents touched close together result in at the AD, and the edge of the materials form a ring current. So this kind of current causes energy losses. That's the eddy current losses. Hysteresis loss also, So because that the current okay, and magnetic field do not change at the same way. Okay, so there is a so-called energy losses. Together is the core losses. In practice, core losses can be represented by a equivalent the core loss can be represented with a resistor. Generally, R core, okay, or Ri, okay. Okay, so remember, once again here, give you a hint is that we say energy losses, right, core losses, but we don't know how to represent it. Actually, in practice, as I just said, any energy losses in electric circuit can be represented by an equivalent resistance. So once again, resistance represents energy consumptions. Okay, so the core losses also can be represented by using a resistance Ri, I here IRA, or R core, RC. Okay, so anyway, so you can use one resistor represent the core losses in the electric circuit. So which will be in the next chapters we will talk about this one. Okay. Okay, so that's the hysteresis losses. Example 2, we have studied in the tutorial sessions in Tuesday. Okay, so here, so in practice, we not just to using the magnetic materials as the core of a coils. So once again, we using the telluride coils as examples. Okay, in many cases, we can have a small card in the rings. So this is the air gaps. So what's the function of the air gap? So the air gap, usually the length of the gap is very small, but the permeabilities in the air gap, as you know, is the mu0, while the permeabilities here in the materials is mu. So because there are still some students write to me, ask some strange questions. So here I once again, in the air here, the air gap is mu0. Okay, but the ring materials, that's mu. Okay, so that's the difference. So the air gap with the permeabilities is mu0, and the other parts of the core is mu. Mu0 constant, small. Mu non-constant, bigger. So as a result, the reluctance in the air, because the mu0 is small, that reluctance here is big, and reluctance here is small. So when we draw this ring into a magnetic circuit, so we have 3 reluctance components. Okay, one is the leakage reluctance, which we already talked, in the last lectures, and so which is the magnetic flux leaked into the air through the gap of the coils. So that's leakage, which usually this is very, very large. The leakage very, very large, and leakage flux very small because the reluctance large, which in parallel with the flux inside the core. Okay, So the flux inside the core in parallel with the flux in the air. Okay, that's in parallel. So for the ring core, the reluctance comes two parts in series, right? Because of the flux running here in series. So one is the core's reluctance, which we call it magnetizing reluctance of the core. And the air gap, it has the reluctance, which is the air gap reluctance. In comparison, that this one, and this one, okay. Okay, as a result, okay, so look at here. So in comparison, because here there's no figure, some students may confuse that. Okay, generally the leakage, okay, the leakage reluctance is very large, very large. So sometimes you can thinking that okay, this branch is open circuit. You can using right coefficient to represent it one in comparison with the other parts. That the leakage flux is very small. Okay, 1% goes through this one, for example. Okay, 10%, right, maximum. Okay, and then for the most of the flux inside the core, and inside the core, the flux, of course, is larger. Okay, for example, this is a 10, this is 110. Okay, this is total 110, 120. Okay, for example, that okay, the reluctance comes from two parts in these parts. Okay, and the gap very large, and the magnetizing part, which is the core materials, although it is longer, which is small actually because the permeability is large. Okay, this is one large, this is small. Okay, so in terms of the flux, that the flux in the core and the flux go through the air gap here is the same because they are in series. Okay, they are in series, so they have the same flux. Okay, that's the relationship. Looking at this circuit and looking at these ring materials, looking at this circuit, okay, looking structure here, and hope you can understand, right, how to draw a magnetic circuit. Okay, try to understanding the relationship between the reluctance, flux, and magnetomotive force. Of course, the magnetomotive force is right supplied from the current times turn numbers of coils. Okay, that's no difficulties. Okay, so therefore, once again, okay, based on what we learned in the electric circuit, the okay reluctance times the flux, that is the okay, magnetomotive force. Okay, and not just this one. Okay, just like a voltage drop, right? So magnetomotive force drop. So flux times reluctance is the magnetomotive force drop. Okay. So for this branch, the flux is phi. Reluctance is Sm plus Sg, right? So the flux magnetic force drop, magnetic force drop is phi times these two. Okay, phi times this. That's the meaning of it. Here, for more easy understanding, so someone, because always right confused with, so magnetic force, we said F here equal to the flux leakage, the total flux, okay, flux leakage times the reluctance leakage branch, right? So here equal. Because they are in parallel, okay, equal to flux magnetism times the total reluctance in the ring. Okay, that's the meaning of it, because this branch are in parallel, So the magnetic force drop here, magnetic force drop here, magnetic force drop are equal, right? Are equal. Do not ask me why, because some students always asks some very strange questions like this. So this is the relationship between them. Then also you can use in the total flux, that the total reluctance. Total reluctance is these two in parallel. So you can further to draw that equal to the total reluctance times the total flux, total reluctance to the flux, and the total flux equal to the leakage flux plus the magnetism flux, right? So this very similar to the Kirchhoff current law and these points, right? So you're looking here, so the total flux equal to the leakage flux plus the magnetism flux. That is the Kirchhoff, right, current law. And F equal to phi L, SL equal to phi M, Sm plus, right, Sg, that is, comes from the Kirchhoff voltage law, right? Similar. This same, right? So the total flux times, the total reluctance. And the total reluctance here is the parallel of these two. The total reluctance here. So someone still can remember, but someone still need me to write down some things here. That is the parallel of the leakage with this two branch, that is the Sm plus the Sg over, because they are in parallel, you know how to get the parallel. Okay, so look at here. So from the Kirchhoff voltage law, for parallel branch, there are potential, potential drop the same. Here is magnetic force fault, right? This potential drop, this potential drop, this potential drop. The potential here, magnetic potential, right? Same is the flux times the reluctance, flux times reluctance, flux times reluctance. Okay? Someone said, oh, here I have no flux. Reluctance, you can look in this side, right? For this branch, look in this side. And then, for the total flux, that is the sum of the leakage flux plus the magnetizing flux. For the total reluctance, that is the leakage reluctance in parallel with the ring reluctance here. The ring reluctance comes from two parts in series. So series, series, in series, then in parallel. Okay. Series in parallel. Okay. And then okay. So here give you, right, the whole image how to analyze a ring circuit. Okay. So for this ring circuit, so that if you have such a magnetic circuit, in this circuit, if you're looking at the magnetic force drops in the three branch, 1, 2, 3, their relationship is F equal to the leakage branch, the magnetizing branch, and the air gap together, and the circuit as a whole. The total flux, the total reluctance. And when you're looking at the flux, so the total flux, the leakage flux, the magnetizing flux, relationship. When you're looking at the circuit total reluctance, so leakage reluctance, in parallel with this branch, but this branch comes from two elements. One is the core material, the other one is the air gap. They are in series, share the same flux, phi, magnetizing. So they are in parallel, so this is the total reluctance. So for such, right, coils, their inductance can be determined based on the definition, that is the N square, turn number square, over the total reluctance. This is the key. This is the key. In previous error call, right? So we can simply write up, the reluctance, the inductance related to the coils, turn numbers, permeabilities mu0, cross-sectional area E, and length L. So that's a simple example, but in practice, you have to get this one from here, because the and the phi is F over S, right? Look at here, once again, recall your memories that the flux linkage, which is related to the induction, is turn numbers times the flux phi. And the flux phi can be determined based on F over S. F is the 9, and L is the phi over I. So as a result, that is the L equal to N squared over reluctance. Reluctance here is the total reluctance of the term, okay, of the coilus. So which is applicable to any coilus, any coilus. So in the practice, we're using this one to determine the inductance of a given coilus, a given magnetic circuit. Remember these points. So the key, right, in the circuit will be determining the reluctance. To determine the reluctance, the key is to determine each component's permeabilities. So, okay, so here give you right analysis about the air gaps in the ring core, their relationships. We draw this circuit. Okay, so you should be able to draw the magnetic circuit for any kind of the magnetic rings like this, or the other types, based on the relationship between the flux in each branch, in each parts in the circuit, and the total flux. You find out that in series or in parallel. It depends on your understandings. Okay, so that's the magnetic circuit analysis here. So we have no any calculations here, but we just telling you about that relationships between each parts of the components. Okay, so go ahead to see another issues. So example 3, actually we have get started in the tutorials, and here so give you more complicated magnetic circuit. Okay, so here give you one more complicated magnetic circuit in practice. So, and we can say so far you learned about the basic concepts and the basic method to analyze the magnetic circuit. So theoretically, you have the capabilities to analyze any kind of the magnetic materials. Okay, just like you learned the Ohm's law, Kirchhoff voltage law, Kirchhoff current law, and power issues. You can analyze any kind of the electric network. Okay, so but time limits, we cannot give you the examples. Similarly, now you have learned about the basic concepts of magnetic circuit. You learned the rules of the magnetic circuit analysis, and you be able to using the basic concepts B, H, S, F, and phi, mu to analyze any kind of the magnetic circuit like this. Okay. Sometimes you need the computer's aids to help you to the calculations. And here, so we give you one examples about electric machines. So in next lectures, you will talk about generators. So you look at here, this is so-called 4-pole machines. Inside 4-pole machines. So there are 4, as you see here, 4 shoe-shaped poles here. This is the fixed parts of the machine, which actually is the core materials, steel materials, which is the iron materials, magnetic materials. So they have 4 poles. For example, on the 4 poles here, you may have the electric coilers. So you have the coilers here. You have the coilers here. You have coilers here. You have coilers here. So on the 4 poles, you have the coilers surrounding it. Apply the current on the coilers, you have magnetic field produced. So because the polarities of the current at one moment on the poles. The magnetic flux has their directions like from north pole N to south pole and go into the core materials and like a loop like this. And also you have parts of magnetic materials goes in a loop like this. And also you have some magnetic materials goes in a loop like this. Anyway, because the core materials here attracting almost 99% of the flux inside the core materials rather in the air. So the magnetic materials and inner parts here, it also is a core materials. Okay, so the core materials. So the magnetic flux inside the cores rather in the airs. Between the pole and the rotors here, the inner cylindric parts, cylindric parts. So there is air gap. Look at here. So here is the air gap. Here is the air gap. Here is the air gap. Here is the gap. So the inner cylindric, right, actually is the axis, which is the rotator, right, which is rotors, we call it. It can rotate, right? Okay. So the flux just like this. By analyze the flux flows inside the core materials here, one can draw an equivalent magnetic circuit for it. So each here represents reluctance, and also the magnetomotive force and flux. So this is one example, electric magnetic circuit. Okay, so actually electric magnetic circuit that very similar to each other in terms of the analyzing a circuit, analyzing equipment, analyzing rules. So that electric circuit rules can be applied to the magnetic circuit. Remember that the magnetomotive force, electromotive force, they are equivalent. Reluctance and resistance, equivalent. Flux and current, they are equivalent. Okay, so when you are applying the current on the poles, change their directions, change their values, then the flux in the cores change their directions, change their values. But one thing keeps by constant, that is the reluctance if the current within certain values. In the BH curve, we show that when the current be smaller, the permeability therefore the reluctance keeps constant. Although, as I said that the reluctance, therefore the permeabilities of the materials is changing with the current change, right? Nevertheless, when the current changes within a small range, for example, says from minus 0.1 amperes to plus 0.1 amperes, the permeability, therefore the reluctance S keeps constant, although it changes. but when the current is small, it is a constant. So which we are making the things be simple. Okay, making the things simple. Okay, remember these points. Okay, so this is one example of the complicated magnetic circuit in practice. Okay, you are not asked to at this moment to analyze this circuit, but you should know the background of this circuit, and in the future when you work as electrical engineer or you're working in the areas of the motor, so you should be able to analyze the magnetic circuit so as you can improve the performance of the machines. Okay, we once again have a summary on the magnetic circuit relating to the power energy issues in comparison with the electric circuit. Okay, so for a ring coils, for a simple ring circuit, okay, for a simple ring coils with no leakage, right? So one can simply to estimate, right? Estimate that the total flux linkage, because now we are trying to talking about the energy issues. So flux linkage used to induce, right, electricity. So the total flux linkage, that is the total flux linkage, that is the numbers of coils that flux in the coils, the flux in the coils based on the rules we learned, that is the proportional to the currents, turn numbers over the reluctance. Or reluctance. So that's N squared over I over S. So furthermore, for a simple ring coils, you can bring in the parameters such as the cross-section area A, such as the length of the coils. Once again, this is the length of the coils rather than the wires, because maybe you do not use the wires there. Okay. So this is the path, right? Magnetic path. Okay, so this is the relation between the inductance and the currents. Okay, flux. That when you apply a current using a source V to apply a coils, the coil has a resistance. Okay, so this resistance, including the copper resistance and the core losses. Total resistance, total resistance. So the total resistance R equal to the copper resistance, because the coils plus the sorry. Okay, this is the wire, the copper loss. The copper loss okay. So when you have a coilus, the coil has a resistance. This resistance, okay, theoretically, the resistance comes from two parts. One is the copper losses, that is the resistance of the wires you used, okay, wire you used, okay, which existing there. So the other one is the core losses. If it is air gap, okay, sorry, if it is air cooled coilus, there is no such terms. Okay, so the core losses resistance. In a few minutes ago, I just mentioned that okay, we can use in the resistance to represent core losses. So the total resistance here, okay, total resistance here, and the copper losses and the core losses. Okay, this is resistance, heating, okay, copper losses. And another point that in the DC case, the core losses be zero because there is no hysteresis losses, no eddy current losses. Remember that? Okay. Okay, get the points? Because next chapter we will use these concepts. Okay. So in DC, this disappeared. So you just have this one. That's why in the example 1, we just taking the resistance here. Okay. So because some students may confuse that. Okay, in that case, we just taking account the wire's resistance. And you still remember that the example 1 wire resistance 1.37 ohms. But here I suddenly say that the total resistance including two parts. Okay, so that's because that in the DC case the core losses resistance be ignored because it is zero. Okay, so there are no conflicts between them. Okay, so therefore this is total resistance, the meanings of it. That is the induced voltage across the coils. This is the total source voltage. Okay, we call it the voltage equations. So the DC, because this one is zero. Okay, so once again, the second term. So second term is the induced voltage. Remember, induced voltage. In DC case, it is zero. So therefore, we just have this part, right? That's Ohm's law. Okay, remember. So we gradually link to the AC, right? So or you can furthermore to write into that's the RILDIDT. Okay, so the L is the inductance. Look at here. So the inductance can link the magnetic circuit with the electric circuit. So linkage, the inductance. Okay, so when the current, right? So not changed. So this term becomes zero. This term becomes zero. Okay. Now we based on these equations to find out, okay, in terms of energy and power. You know that in the DC circuit, the powers is the voltage times the currents. So voltage times currents. So you can find that is the RI squared for this term, and for this term is the LIDIDT. It has a unit of the watt. That is because it's powers. Okay. Furthermore, you can write into that the powers is the current square resistance. And look at here. So I still current square. You know the differential and the integration, right? So we can change, right, this part I into it, right? So DI square, okay, that is the 2I DI, right? So you change this I into the differential variables, differential variables, you will find this one, because L is a constant, suppose. So this is what? Power change rate, right? This is power, this is power, this power. This power integration. That's energy, right? Okay, so this is the energy, right? Okay. Energy change rate is the energy change rate, right? Energy change rate is the power, right? Because this is powers, this is powers. Okay, so this is the energy. Energy over times, that is the powers. So this is the energy in the coils. Okay, so this is the magnetic field energy in the coils with the current I. Okay, understand, right? Okay, so the total energy, energy stored, so which is the this is energy, okay. So therefore, this is the energy, and this is energy, which is the joules, okay. Because this is power differential, that is the energy, right? Sorry, energy differential, that's powers, okay. Time differential, okay. Time derivatives. Okay. Furthermore, based on this one, okay, so the powers, the energies in the magnetic energy in the coils, can be related to the Li squared, over 2, or the phi F over 2, or the I phi over 2, the same. Okay, the same. So now you know how we got these formulas. They just to compare the heating energy in the electric circuit with the magnetic field energy in the coils in comparison with each other. We can find out that this term is the energy, which is the total energy in the coils. Okay. Furthermore, energy density, energy divided by the volume of the core, that is the energy density. What's the volumes? What's the volumes of the coils? So, for example, for the ring coils, its cross-section area A and the ring length, that is the volume, right? Volume. So cross-section area A, length L, volume. So energy over the volume is the energy density, which is BH over 2. You can prove it easily because we write down here. So I phi, because the phi equal to the B times A. The F is H over L. Once again, Okay, so H equal to F over L, B equal to phi over A. Bring in, that's this one, right? That's this one. Okay. But anyway, so all this, right, based on the same principles. All these formulas based on same principles. Okay, that's the energy issues. Okay, so now you should be able to link the magnetic circuit parameters to the energy issues inside the magnetic circuit. Okay, so you can, based on such analysis, to find out the relationships between the B, H, F, phi, L, I, and furthermore the permeability mu, and so on. Okay, so this is electromagnetic circuit analysis. Electromagnetic circuit. This is a typical electromagnetic circuit. Okay. Okay, so go ahead, right? Go ahead to another right concepts. So far, what we learned is about the DC circuit. DC circuit, right, means that the current keeps the same directions, normal change. Okay, so there the induction issues disappear. But when there is change of current, there is induction. That is the okay. So now slightly apart from the DC. Okay. So as I just said that. So when there is a change of the current, there is an induction void, right? So hence the effect of the inductance L should be considered in the circuit. Okay. So this is the points. Okay. Okay. Highlights. Okay. So as you know that for any electric circuit, they involves currents. They involves, right, wires. So wires can be seen as a kind of the, right, okay, coils. So when there is current, there is a magnetic field surrounding the wires. So the wire itself has inductance, no matter what wires you use. Okay, even you use the superconductors, there is, okay, inductance. Okay, so and in the DC circuit, at least you have the switch on and the switch off process of the circuit. When you switch on, the circuit closed. The current increased from 0 on to certain values. So this process, we call it transient, okay, process. So in the transient process, both the resistance R and the inductance L affects the currents. That's what I said here. Okay. In the DC circuit itself, the L inductance, okay, does not produce inductions. That is the balanced or, okay, process, steady state process. Okay. Now we considering that the switch on or switch off process in a DC source connecting to a resistor R, okay, and an inductor L. So anyway, so now you have learned about the inductance. You should consider for any machines or any component, it has the resistance R and inductance L. Whether okay, the inductance L affects circuit or not depends on whether the current changes or not. Okay. So in general, the Ohm's law or the voltage equation in a general electromagnetic circuit can be written as the source voltage V supplied to the resistor and also supplied to the inductor. Okay, resistor, inductor, source voltage. So the Ri is the voltage drop across the resistor. The LIDT is the induced voltage by the inductor against the source, always against the source. Okay, against. When the current no change, this term be zero. That's the DC circuit. That's the Ohm's law. But here is also the same things. The Ohm's law. Actually, this is also Ohm's law. Okay. In the next lectures, next chapters, we'll talk about this one. Then you know that for such differential equations, suppose R and L are constant, one can find out the general solutions, which general solutions, which is the general solution is the coefficient A, this is coefficient E minus the L change with time t plus okay, so for this equation, it has a general solution that is the coefficient A, E minus R over L T. This is the exponential right solutions, and plus the B, another constant. The two coefficient A and B, should based on the boundary conditions of the equations. For this is general solutions of this equation. If you're looking into some of the differential equation solution in the network, you can find out this one. And for the switch on case, there is two conditions. When t equal to 0, the current is 0. Am I right? Then when t is very, very large, long times later, the current is stabilized at level V over R. Say when times very, very longer later, because the di no change. Long times later, this term becomes 0. Right? So the current stabilized at a certain level, that is the total voltage over the R. Voltage over R. So based on these two conditions and 0 time t equal to 0, there is condition. T equal to very, very large, this is another condition. We can determine the A and the B. So we found the A and B actually, look at it here, is this solution, final solutions. When t equal to 0, E power 0 is 1. 1 minus 1 is 0. So current when t equal to 0, okay. Okay, so based on these two boundary conditions and these general solutions, one can find out the case for a switch on process of a circuit. So when you switch on, the times, the current. So the DC circuit switch on, the current has a transient process like this. The process, how fast this process is, depends on the inductance. If the inductance be zero, look at here. If the inductance L be 0, this will be small, 0. This will be 0. Okay, exponential, right? Okay, this will be 0. Okay, if the L is very large, look at here, L is very large. So this one is very small. Okay, they take a long time to making the current go to the stable values. Taking very long times, go to the stable values. So the larger of the L, the longer of the transit times. Okay. So this is the switch on process. Similarly, we have a switch off process. The condition equation is the same. Condition is different. Okay. Okay. So anyway. So for the previous case, you can bring in some of the figures to some calculations. For example 1, 2, and 3, if you apply a voltage 10 volts batteries with the internal resistance 0.1 ohms, you can neglect the connecting cable resistance and inductance. You can plot the transient rise in the current for switch on each of the coils when the magnetic circuit is described by example 1 to 3 above. That means in the example 1 to 3, you have the resistance R. You have the inductance for example 1, example 3, example 2. Okay. So there, for a given voltage, for example, 10 volts, and the source 0.1 ohms, then the wire resistance 1.37 ohms. Okay. So you can calculate how does the current change against the times. Okay, so we do not repeat that because the example 1, the wire resistance 1.37 ohms, that battery now giving 0.1 ohms in series with the wires, and the current voltage is given here, and inductance in example 1 0.32 millihenries, for the 5 amperes. Example 2, that is the 78.9 millihenries, when current equal to 5 amperes. Example 3, that the reluctance will be small, that is 1 use, which will be about and 5 amperes. You can estimate, which probably is about 20 millihenries or something like that, or any values else. So you can do it as an exercise to highlight the difference between the example 1 and example 2. Actually, because their inductance is different, their transient phenomena slightly different. And also, you can estimate that how much energy is stored in the magnetic circuit at the different current values. Okay, do the example 4 as an exercise. Okay, so also you can analyze the example 4. We say it is example, right? But actually, so you can analyze simply based on the above circuit. When you consider switching the above stated current off, then what happened to it? Okay, so we can discuss further in tutorial sessions about this one. Okay, now we come to another concept, that interactions between the coils. So far, okay, we just learned about the one coils. That means the coils apply with the current, produce magnetic field that induce voltage on itself. Okay, so far we learned that the coil itself induction issues. That is, the coil produces flux that induces the voltage on itself. Okay, that is the self-induction. Self-induction. Okay, they produce flux. The producer, okay, of the flux, and the receiver of flux, the same. Producer. Okay, producer, we have the flux, phi. Okay, producer, we have N1, for example, okay, times current I1 over the S1. Okay, receiver, okay, receiver. Okay, total flux. Okay, that is the N2 times, okay, the flux 1. Okay, okay. Okay, now let's consider another issues. So if we use one coils, coil 1, which has 10 number N1 with a current R1 and a reluctance S1, to produce a flux 1, then this flux come into the second coils. So in the second coils, the flux linkage to the second coils, that is the second coils N2 times flux 1, that is N2, N1, R1, S1. Wire in K. So this result in, okay, look at here. So which can be, right? So right into the L, okay, 2, 1. Okay, L to 1, current 1. current 1. Look at here. So if we have two coils, the coil 1 produce flux coming into the coil 2 that induce voltage on the coil 2. Okay, so which can be right into the N1, N2, R1 over S1. Okay, so we can similarly to the self-inductance, we can define a mutual inductance L21. That means producer 1, receiver 2. 1 due to current 1 on the current 2, due to current 1 on the coil 2. Okay, so this is the mutual inductance. That is the N1 over N1, N2 over S1. Okay, in comparison with the self 1. Self-inductance equal to N squared over S. Okay, the mutual inductance, this is a mutual. Okay, mutual inductance equal to N, sorry, the N2 times N1 over the reluctance between 1 and 2. Actually, you can compare these two. So the above one is the self-inductance, which is the term numbers N squared over the reluctance of the coil itself. So receiver 1N, producer 1N, N squared. Now in this case, two coils together, producer is the coil 1, that is N1. Receiver is the coil 2, that is N2. As a result, there is an inductance between the coil 1 and coil 2, which has a mutual inductance, which is the N1, N2 over the reluctance between the two coils. That's the concept. Okay, that's the difference here. Unit the same, but look at her difference. Okay, so now you're understanding the N squared meaning. One is the producer, one is the receiver. For mutual one, producer, receiver different. For the self one, producer, receiver the same. You earn monies, you spend the monies, right? Okay, but now you actually you spend the money from your parents. That's the same thing, mutual one. Okay. Now, so based on sidereal comparisons, it is easy for you to understanding the relationship of the two coil issues, the coils coupled. So when you have two coils, one coil is produced with the current R1, voltage V1, produce flux phi1 that come into the coil 2s. So therefore, there is due to the coil 1's flux, coil 1's flux coming to the coil 2s, which changing with times, induce voltage on the coil 2. Okay, and there is a magnetic flux path between the coil 1 and the coil 2. So the path may be simple, may be complicated, for each coils. So there is a reluctance between the coil 1 and the coil 2. So the equivalent here, once again, is a concept equivalent cross-sectional area of the flux path. Equivalent length of the flux path. And the core materials, the path materials permeability. Of course, here is talking about each component. The coils may be consists of several components. You have to use the network concepts to the calculations or to the analysis. Okay, so in such a way, as I just talked here, we can further define a mutual inductance. Okay, generally, the mutual inductance tends to use in the M representative so that it is be distinguished from the self-induction L. So M here stands for the mutual inductance. So similar to the self-inductance, mutual inductance. Okay, so once again, for a simple coils, that mutual inductance is the turn numbers N1 times turn numbers N2 over the mutual reluctance. Okay, so furthermore, so you can very similar to the simple self-reductance. Okay, so N1, N2, the mu is the permeability of core materials. The A is equivalent cross-section area of the path, equivalent the core length. Okay, here it's just the concepts, right? Conceptual expressions. So the formula here is not exactly for the calculation, but for expressions about physical meanings of each of the parameters here. Generally, the mutual reactance, inductance, mutual inductance. Here we just inductance. Next lecture, sorry, we will talk about reactance. Okay, so inductance, mutual inductance, from 1 to 2, from 2 to 1, the same. Of course, right? So how much 1 to 2, how much 2 to 1, the same. Okay, producer. That's the mutual inductance of couples, which will be taught in detail in the transformer part, because transformer based on the mutual inductance. Transformer based on mutual inductance. If the turn numbers N1 and N2 the same, then the inductions between the D channels will be the same. Now, so once again, we can extend the voltage equation from 1 coils to 2 coils to 3 coils to 4 coils, 5 coils. Here, we're just using the 2 coupled coils to express the equations, voltage equations. For a linear, what does it mean by linear? Means the inductance, linear means inductance is a constant. Okay, for a linear double excited coil systems in the air, the constant inductance means the constant in the air because the air permeability is a constant. So linear means that constant inductance, constant permeabilities. Usually in small current cases, right? For the magnetic materials, it is linear circuit. Okay, for a linear double excited coils, 2 coils in the air, the voltage equations can be expressed when the source voltage of V1, coil 1, applied voltage of coil 1, and the voltage drops in the resistance of the coil 1. So once again, the voltage here drop. The coil 1 is not just the copper, but also has some of the core losses. But maybe the core losses is smaller. It doesn't matter. But this is the total voltage drop in the resistance issues. This is the self-inductions. The coil 1 coil 1, I1 produce flux that running in the coil 1. So this is self-inductance, which is N1, N2 related. Okay, because the path the same. When these two coils couple together, the path the same. So the reluctance the same. And so this is the coil 1's current induced on the coil 1 itself. The here is the coil 2's flux coming to the coil 1's that induce the voltage on coil 1's. Okay, this is N1 times N2 over X. Okay, now you understand the difference between them. Okay, self-inductance, mutual inductance. Okay, so the reluctance between them the same. This is I2, this is I1. Self-induced voltage in the coil 1, okay, by coil 1. Mutually induced voltage in coil 1 due to the current in coil 2. Similarly, on the coil side, so this is the applied voltage in coil 2. This is voltage drop in the resistance of coil 2. This is the self-induced voltage in coil 2. This is the mutually induced voltage in coil 2 due to the current in coil 1. Okay, so you have this is N2 squared over S. Okay, this is the same. Okay, so self-inductance coil 2 is the coil 2 squared over S. And mutual inductance coil 2 to coil 1 and coil 1 to coil 2 the same. Okay. The mutual inductance can be positive or negative. Okay, because that the magnetic flux produced in the coil 1 can help or strengthen the magnetic field produced by the coil 1 itself, or opposite, the magnetic field produced by coil 2 or coil 1. So they may opposite, right, to each other, or additive to each other, supporting each other or against each other. Okay. So this is cell 1, this is mutual 1. Mutual 1 here, maybe the resulting may be against or plus or minus, plus minus. Okay, that is possible. Okay, depends on how the coil is oriented, right? Orientation of the coils. This is a coupled coils. Now we have the self-inductance, the mutual inductance, the magnetizing inductance, the leakage inductance. Okay. The self-inductance, we have also plus leakage inductance plus plus magnetizing inductance. For the coil cells, okay, so far you should understanding the relationship between the inductance. So we generally say inductance, but in details we have the self-inductance of a given coilers. The self-inductance is the total inductance of coilers. In the previous examples we're showing you that because the flux has magnetizing flux and leakage flux. So the inductance corresponding to the magnetizing flux, magnetizing inductance parts, and leakage inductance parts. Total inductance of the self-inductance. And then mutual inductance. So between any two coils, there are so-called mutual inductance. Anyway, when there is magnetic field, there is inductance. The way there is current, where there is magnetic field, where there is inductance. So the inductance has the self-inductance, has the mutual inductance. For the self-inductance, there are leakage inductance, there are magnetizing inductance. And the inductance, mutual inductance, can be additive one or subtractive one, depends on the rotations of the two coils. Anyway, so now we have many types of the inductance, but the nature of them the same. That is the flux cross a coils. Induced voltage on the coils. Flux cross the coils, induced voltage on the coils. So this example 5. Here we have a simple explanations on it then. So suppose you have two coils here. So coil 1 and coil 2. Suppose look at here. The winding directions of the coil 1 and coil 2 the same. For one coil same. Then we have the same currents go through the windings. The flux in the coil 1 and flux in the coil 2 has the same directions. So there are additive. For coil 1, it has a self-inductance L. For coil 2, it has a self-inductance L, because they're same, and the mutual inductance between them is the N. When these two coils in series, then the total inductance is 2L plus the A, because L equal to N, 1L equal to N square over S, right? N equal to, there are some little leakage, right? There is a coefficient. For example, we have a coefficient A, times the N1, N2, but N1, N2 is the same, right? N1, N2 is the same. Okay, when they are in series, the total inductance equal to okay. So if the leakage is almost be zero, we ignore leakage. There will be n, okay, 2n squared, right? 4n squared, right? Okay. Okay, so now another one is total flux. Flux 1, flux 2, flux 1, 2, flux, right? 2, 1. Okay. L, because the current is the same, right? L in this case, because the coil, right, have the same current, okay, has the same current, okay, in series. So look at it here. So the total flux when they're in series, okay, each of the coils has a self-reluctance, inductance, okay. So self-inductance and a mutual inductance. That's the solutions of it. And similarly, for this case, if the coil 1 in this direction, coil 2 in this direction, the magnetic field will be, okay, opposite to each other. For coil 1 and coil 2, okay, coil 1 and coil 2. So the total flux for the coil 1, okay, is the coil 1 minus this one. In the coil 2 is the coil 2 minus this one. Okay. So that's the, okay, total flux. As a result, there will be, okay, such issues. Okay, you can change the directions here and here, right? Okay. So when the opposite, minus and minus, okay, because of the directions. Okay. So in such a way, in practice, we can use in such a way to make a big resistor with small inductance. Okay. Okay. So this is actually is, okay, repeat, right? Okay, in the, okay, example 5. Okay, you can analyze, okay, based on the same, right, concepts, okay, using the total flux concepts. Total flux concept. Okay. Because total flux linkage is the total inductance times the current. Okay, remember, so when you have the magnetic circuit issues, for each component, for the total circuit, okay, using the total flux linkage concept to analyze the inductance issue, right? So when you consider one part, that part total flux linkage there. So because the total flux linkage is the total inductance times the currents there, okay, times the currents. Okay, so use these concepts apart from this concept because this is the definitions, okay, of the inductance and the flux linkage. Okay, similar. Okay, so anyway, so in summary, if we have two coils that not the same, we just can analyze the two conductors, two coils with the same. Okay, if they are coupled together in series, additive, in series, subtractive. So if the coil 1 has a self-inductance L1, coil 2 has self-inductance L2, and there is a mutual inductance between the coil 1 and the coil 2, M12, O21, they are same. Then, when they are connected in series, okay, connecting in series means that when the current right in series, applied in series, then the total inductance will be like this. The total flux, actually total flux, flux 1, flux 2, plus the mutual flux. When they are connected in series, subtractive, then the mutual flux will against the self reactance. Okay. Then the total inductance in the coils will be the self-inductance 1, self-inductance 2 minus the 2 mutual inductance. If there's no leakage, you can imagine the L1, L2, and the mutual one very, very close to each other values because the mutual is N1, N2, okay, N1, N2. So the L1 is N1 square, L2 is N2 square, and N1, N2. So once again, I remind you that, so that you can comparison at any moment. This is N2 square. Okay, so the self-inductance always the N1 self-inductance, N1 square over the reluctance, N2 square over the reluctance, N1 and N2 together over the reluctance. That's the difference. Okay, proportional to here, I just say. Maybe there are some leakage, right? Okay, proportional to each other. Okay, so this is their relationships in practice. Okay. Okay, so this is one example of the pair of the conductors in practice. As you know that okay, in the electric circuit, we always use one cables with 2 cores, or with 3 cores, or with 4 cores, even 5 cores. Okay, there are carry current okay, in different directions or different phase. Okay. Suppose that okay, we have one pair of the circuit that at any moment we have the current in one conductors is good, okay, go to the load. On the other conductors is apart from load. Okay, so there is opposite directions in 2 conductors. Opposite, right? So one conductor, the other conductor. So you can imagine the magnetic field in one conductor's direction, okay, in another conductor direction, okay, one direction. So you can imagine that the internal flux surrounding the wires, there have cancellations between them because they are opposite, okay, opposite, because the current are opposite. Okay, so between them, the flux is very small. Okay, very small. Between them, very small. Okay. But surrounding them, okay, they are bigger. Okay. Okay. One is in this direction. One is in this direction. The other one in this direction. Okay. In this direction. In one in this direction. In this direction. Okay. They are opposite to each other. So therefore, based on the okay, you can imagine. Okay. So when in the air, this is the okay, you can analyze the flux surrounding the wires for okay, infinitely longer 2 pair of the wires close to each other. One can okay, analyze the circuit to get the inductance. Okay. Once again, probably at this moment, it starts difficult for you to get a cycle inductance. So anyway, by doing the magnetic circuit analysis, one can find out the inductance okay, per meters per pair per meters between these 2 conductors okay, can be found out like this. Okay. Here is the permeability okay, of the air actually. Okay. So here is log E, that's due to the external leakage flux. Okay. This is due to the internal flux density. Okay, internal flux density in the conductors. So imagine okay, D is the separation between the 2 conductors, and small d is the diameters of conductors. So when the diameters of conductors are very small, and okay, when the separation is very big, there are very big leakage between them. Okay, so therefore the inductance okay, will be bigger, so one. Okay, when they're very, very close to each other, even when they're close to each other, that means when the d equal to 0, so the external magnetic flux will totally canceled because the directions, okay, suppose this conductor and this conductor overlapped. So the external flux will be 0 because the current, one is inside the paper, the other one is outside the paper, right? So their total flux externally will be 0. Okay, will be 0. Okay. Similarly, we can find out the inductance for 2-core materials, for 3-core wires, for single-core wires, which okay, result in the okay, inductance, therefore the impedance, therefore the voltage drops in the AC circuit, not DC. In the DC, inductance not functions. In the AC, inductance okay, causes inductions that voltage drops. Okay. We have the 3 conductors, okay, 3 conductor case, the current not exactly opposite, okay, they have a phase difference, okay, so different from the DC case, which will be discussed, learned in the chapter 2, chapter 3, and chapter 4. Okay, so this is the tutorial example that we will talk in the next week. Okay, so that's the end of the chapter 2. Chapter 2, where we learn about the magnetic circuit. Once again, remember the permeability mu, which is changing with the current. The analysis of the circuit, of the magnetic circuit, the key is determining the mu. Therefore, you can determine the reluctance and you can determine the inductance of the circuit. That's the key issues. Do not forget that. So that's the end of today's lectures. If you have some questions, we have several minutes. You can write to me or you can voice out. Doesn't matter. Now I'll stop the recordings.